Welcome to the Ghost Geeks. I'm Chad, and today we have part 3 of our 3-part series on structured light sensors, better known to investigators as the SLS camera. Today we are going to really dive into the technical aspects of SLS systems, how they work, and how to start coding your own interface from the SDK or API from Microsoft. Now that we've discussed some of the basic operations of the SLS camera, let's talk about a different system that is now being used called the XLS system. The Kinect version 2, or XLS, is not a structured light sensor. It's a time-of-flight sensor. Time-of-flight systems use the time it takes for the light to travel from the projection to the object, and then back into the camera to calculate the depth of the object being measured. This system does have some advantages over the structured light sensors in things like cost, compactness, and range sensing. But the structured light sensor is more accurate. What does this mean for you? Well, it means a few things. First, the XLS system overcomes the focal error problems the SLS system has. This means the XLS system can look into long, dark hallways and measure all the way down the hallway, since the sensor is measuring the time it takes for the light to return to the camera and not the distortion between the projection plane and the camera angles. Second, this does mean that the XLS camera, paranormally speaking, does not detect atmospheric disturbances as well as the SLS system. This doesn't mean it can't detect them, but we must be very cautious when using the XLS system anywhere outside or in locations where the elements are intruding into the space. The way the XLS system would detect atmospheric distortions would be in depth perception rather than a shape. Depending on your philosophy on the subject, this could be good or bad. Leave a comment below and let us know your take on that topic. Okay, we're about to get really geeky here. Let's discuss the theory of phase scanning and how this is being applied to the structured light sensor and similar technologies. So the structured light technology is built upon trigonometry, where we use a known distance, say of a laser, that's one angle. The other comes from the fixed angle of the camera looking at the laser dot. This line gives us the side, and now we can calculate the distance to the laser dot. This is all good for a point, but cameras do not need to focus on a single point. They can see the entire scene. This means we can scan light into the scene and scan the line. Or better yet, we can use multiple lines and track them all at once. This is structured light scanning. Three-phase scanning is used to overcome two problems with the basic functionality of structured light scanning. Imagine, if you will, you are projecting a gradient from white to black. In structured light sensing, the brightness of the given point corresponds to the angle of the projector. But there are inherent problems with this. One, there are only 256 possible angles due to bit rates of most cameras and projectors. And two, the reflectivity of the scene isn't known or accounted for. And lastly, the way the light intensity drops with distance or the light absorbing properties of the materials of the scene, we don't know that. The way phase scanning overcomes two of these problems is by projecting multiple gradients that are slightly offset from each other. The light's intensity drops with each gradient acting like a scaling factor on all the light at a given point. This also allows the color in the scene to be a factor of intensity as well. And lastly, by repeating the gradients as waves, we get opposing lines that don't have the same brightness. Unfortunately, this causes us to lose the unique angle identification on each wave. But we get past this with phase unwrapping, which assigns the number from one stripe to the next as they pass by the same position. To correct this, we use the technique of three-phase scanning consisting of the mathematical patterns here. If you're an electrical engineer, this will look like three-phase electricity with each phase being 120 degrees out of phase from the previous phase. Now, let's look at how the Kinect system finds the body or skeleton in the images it's scanning. Finding the body position is a two-stage process. First, the structured light sensor builds the depth map we've been talking about. Stage 2, body parts are inferred using a randomized decision strategy that's constantly learning from feedback loops. Since we've basically been talking about the first stage in the past two videos, we will focus now on the machine learning portion of this process. The base of the SLS software has preloaded over 1 million training examples featuring dozens of body types with varying parameters captured from a motion captured system. The software uses these reference images to render more images from the SLS system. The next step of the process involves a system like a decision tree or an algorithm. to make decisions on random sample points from the series of images. A very simple version of this looks like this. Does this pixel exist in an offset distance? The formula that creates the tolerances for that decision is based on the information gain, G, expressed as the entropy of H. The SLS system can't run these decision steps for every pixel. That would cost too much in processing power and memory. Instead, the SLS system takes a random sample of 2,000 points per frame. Remember, we're running at 30 frames per second, or in this case, 60,000 data points a second, and uses those points for the calculation tree. After the points in the frame are gathered, the SLS system uses the mean shift algorithm to compute modes of probability distributions. And some of you said we would never use statistics after high school. The algorithm looks for the densest cluster of distortions and then applies the decision tree. The results are very accurate. All in all, the Kinect system uses probability, statistics, multivariable calculus, linear, and topological algebra. Math is awesome, people. Lastly, let's take a brief jump into some of the tools Microsoft provides in their Software Development Kit, or SDK, that we can use without any code knowledge. First, if you have the Kinect 1.0, then jump over to this website. If you have the Kinect 2.0, then go here. Both of these links will be in the description. If you're interested in more code examples or practice modules to learn coding the Kinect, simply type in Kinect SDK in the search bar of Microsoft.com. After you download and install the version that best fits your Kinect device, you can open up the Kinect SDK and Kinect Studio. Inside, you will find a number of pre-built functions that will operate with your Kinect. These modules can be called by code to run and operate in your own project without having to recode any of the functions. It's like a quick start to your own Kinect SLS interface. The Ghost Geeks are creating code all the time, and eventually we will be launching our own Ghost Geeks GitHub to allow for open source functionality of many of our own tech builds. I hope you have enjoyed this series on the SLS camera. Remember that next week we'll have our live question and answer session at 7 p.m. on YouTube. So bring your questions, comments, and all your favorite stories about your best SLS captures. If you have SLS evidence you'd like us to review and share during our live discussion, you can send that to us. Just send us a message and we'll send you a link for an upload. And lastly, be sure that you're subscribed to our channel so you don't miss out on the great schedule of tech videos we have coming up. Until next time, I'm Chad with the Ghost Geeks, and remember to talk nerdy to me.